Please listen carefully.
Hello and welcome to GasGasGas. This is the best podcast for the FRCA primary exam. Our goal is to fill your brain with all this highly useful information. You might be in the gym right now, commuting, or ironing your scrubs. Regardless, the revision is eventually going to end, but for now, expect facts, concepts, model answers, and the odd tangent. Make sure to check out GasGasGas.uk. The show notes there's loads more detail. Make sure to like and subscribe. Anyway, buckle up, get ready for your mind to be bent into a new shape, and let's get on with the show. Hello everyone, and welcome to GasGasGas. Today's episode is going to be on the joys and delights of isomers. We're getting back into the nitty-gritty of that pharmacological knowledge that we all require. I certainly use this on a day-to-day basis. When you pick up your levobupivacaine versus your bupivacaine, although I can never seem to find enough levobupivacaine. Everyone just seems to have bupivacaine in the cupboard most of the time. Right, what are we going to perhaps know by the end of this episode, once you've maybe read the show notes and then done some Googling? I remember that this never seemed to want to stay in my brain when I was studying for this here exam all that time ago. So we're going to try and put it in your brain. It might stay there. We're going to look at isomers, stereoisomers, enantiomers, and diastereoisomers. We're going to try and explain why these drugs seem to have a bit of a different biological activity. And most importantly for the exam is to have examples of each of these things, because that's really what they're going to ask you. Tell us about this. Give us an example. But before we get into the nitty-gritty of that, if anyone is unexpectedly flush with cash, feel free to donate to the show, help keep the lights on. As you might expect, podcast hosting, web hosting, domain names, none of that's free. But admittedly, the incalculable fame that comes with this, in certain circles, is also deeply intoxicating. Right, so what on earth is an isomer? Well, having a quick fire definition of this is always going to make your life easier. There's a few key words to squeak in. They are compounds. They have the same molecular formula, but a different atomic arrangement. If you were to scribble this out on paper and you wrote down that you had 3 carbon atoms, 2 hydrogens, a chlorine, 5 fluorines, and an oxygen, but then you rearranged them in 2 different manners, you would have isoflurane and N-fluorane. But an isomer isn't just limited to isoflurane and N-fluorane. A bunch of molecules are isomers of different subtypes. Important not to get carried away. So, types of isomers. You have structural isomers. These are positional and tautomeric. You have stereoisomers. These can be geometric or enantiomers. And some enantiomers can be diastereoisomers. And we're going to go into each one of these in turn. These subtypes. So a positional isomer, we're talking are N-fluorane and isoflurane. Similar backbone, but molecules attached to that backbone are laid out slightly differently. The other key subtype of structural isomers are tautomers. These are relevant in anaesthesia because thiopentone is a true tautomer and midazolam is masquerading as a tautomer. Then we have stereoisomers. Now, we all know that stereo sound is because it's got a left and a right, and therein lies the giveaway that there must be 2 things sort of happening here. There are 2 subtypes, generally speaking. Geometric isomers. This is our cis-trans isomers. Great example being mivacurium, and our enantiomers, which are molecules that if you mirror image their layout, you cannot superimpose one upon the other. And don't worry about this, guys. We're going to go into each one of these things in more detail in just a moment. The classic example of an enantiomer would be bupivacaine. You know, you've got bupiv, which is a racemic mixture, and then levobupivacaine, which is the enantiopure levo enantiomer. The most important thing to remember in terms of what makes an enantiomer and enantiomer is that it has a chiral center. This is a molecule which has 4 other molecules bound to it that ends up being the linchpin that defines what the 3D structure could end up being. Again, we're going to go into more detail in a moment. A subtype of enantiomers are diastereoisomers, and this is because you're allowed more than one chiral center in a molecule, but as you can imagine, it's going to create a bunch of headaches if you have multiple points, which could lead to multiple different configurations of atoms forming different 3D molecular shapes. Bamboozling. So we're just going to go through each of these now in turn in slightly greater detail. Although remember, guys, that positional isomers, same set of molecules, just with molecules ranged differently attaching to that backbone. Isoflurane, N-fluorane. It is important to note that just because they have all the same molecules doesn't mean they have the same properties. So N-fluorane boils at 56.5 degrees Celsius, whereas isoflurane boils at 48.5 degrees Celsius. And their saturated vapor pressures differ by 9 kilopascals, N-fluorane being 23 kilopascals and isoflurane being 32. Now, I'm not going to go into oodles of detail on volatile anaesthetic agents in this episode, but don't you worry, folks, we are going to do all of the volatile agents. We might even dabble in ether. We're going to chat halothane for historic interest and xenon just for a laugh, I imagine. But anyway, not yet. I doubt xenon will be in the exam. You can always just skip over that episode. I'm probably doing it more for me than you. Anyway, anywho, tautomers. So a tautomer is a form of structural isomerism whereby the nature of the structure can change dependent upon the environment that molecule is in. The typical environmental change is acidity. So are you in a more acidic environment or a more alkali environment, and what does that do to the molecule? We know that environments influence ionization, and you could think of it a little bit like that. The key example is sodium thiopental. When it's dissolved in that water for injection inside its ampule, it's got a pH of 10.5, and this is a quite heavily ionized molecule at this pH, and that means it's nice and water soluble. When you take that water soluble agent and squirt it into someone's vein, it is introduced to quite a considerably more acidic environment compared to the 10.5 in that ampule. The key words here, if you're in an exam, is keto and enol. So the enol forms of barbiturates are really water soluble, and that's what you get when it's got that nice alkali pH in the ampule, courtesy of the sodium bicarb, whereas the keto form is the uber lipid soluble version. How does it make this transition between water soluble happy enol and lipid happy keto forms? It does this by transferring a hydrogen ion from the sulfur atom to the nitrogen atom, changing the shape of the molecule and making it superlipid soluble. Now, what about midazolam? As I mentioned earlier, that it seems to masquerade as a tautomer, and this is because, once again, in the ampule, it lurks at an acidic pH this time, and is nice and water soluble. Well, then you chuck it into the plasma, and now we're less acidic than we were. And this ring, because we all know about benzodiazepine rings, that is open whilst it's in the ampule, closes once it's in the plasma. It ends up actually displacing a water molecule from the molecular structure of the midazolam when it forms this shift from an open ring to a closed ring. If you were to compare how many carbons and hydrogens, etc., there were between these two molecules, it would be different, and therefore not truly an isomer. No one's going to ask you about that, though. And if they do, it means that the examiners are really getting to the end of their questions they could possibly ask you, and you've definitely passed that station at least. So I think it is worth, if you're not driving your car, getting up a picture of different types of isomers. There's loads of great diagrams on loads of different websites, because now we're thinking about stereoisomers. Remember, these are the geometric subtype and the enantiomers subtype, or enantiomeric. Geometric isomers are our cis-trans isomers. Cis means this side of, trans means the other side in Latin. For these to occur, you tend to require a pair of carbon molecules that have a double bond. This double bond means that it cannot rotate around this point. However, as we know, carbon molecules can have up to 4 different things bound. If we've got a double bond, 2 of those binding points are taken up, but there are 2 free binding points which could take an amino group, etc., etc. If we imagine we've got our 2 carbon molecules, our double bond, and then we have a hydrogen molecule attached on each of these carbons, and now we've got, let's just call it a carboxylic acid group, the COOH, Q minus thing. You have one of those bound on either end. If we imagine an upper binding point and a lower binding point, you could have the carboxylic acids both on the top, both on the bottom, or one at the top and one on the bottom. And this one on top, one on bottom affair on these opposing carbon molecules with the double bond between them is our trans molecule. Whereas if it was those acid groups are both on the top or both on the bottom, that's this side, same side, cis. The great example of this is mivacurium. What about enantiomers? This is probably the biggest and broadest group. Enantiomers, enantios, Greek for opposite, and this is because it refers to molecules that are the mirror image of one another. If you had an equal mix of two molecules that were the mirror image of each other, you have a racemic mixture, and that's bupivacaine. The key thing with these molecules is that they have a chiral center. Now you can then end up with molecules with more than one chiral center. We're going to go there in a moment, but we have a single chiral center, and we'll call it a carbon molecule, but it also could be a sulfur molecule or a phosphorus molecule. We're back to our friendly carbon molecule. It has 4 binding points. These 4 binding points, each with an atom bound to them, ideally a different atom for the sake of this. We know that atoms all have fields of electrical charge around them, and these molecules want to try and reach some sort of equilibrium where they're only invading each other's space just about the right amount. You can imagine this a little bit. If you've got 3 balloons of varying size and you hold them all together and try and pull those cords, so you draw all those balloons right next to each other, they will figure out a position that means that they can squish right next to each other as much as they possibly can. They settle into an order. And when you have these atoms hovering around a carbon molecule, they will settle into an order. You can imagine this layout a little bit like a triangle-based pyramid with that carbon atom inside the middle of the pyramid. So you've got a molecule at the top and then a molecule into 3 corners. An easier way to think about this is, again, if you're not driving, because you need your hands for this, if you look at your hands both palm up, they're a mirror image of one another. If you then try and put one hand palm up on the other, you can't line your fingers and your thumbs up. It just doesn't work. And we also know that one hand tends to be better at one thing than the other, or if you're trying to twist a doorknob, sometimes it's easier with your right hand versus your left hand. These hands, these opposites, can have slightly different functions and characteristics. Now, I'm assuming everyone has all their fingers left. If you've got terrible frostbite or you were a carpenter, I'm sorry to have singled you out. How do you classify enantiomers? We've heard of levobupivacaine, haven't we? But we've also heard of S-ketamine. Oh, what's going on there? So that's 2 different classification systems. System 1 involves shining polarized light through your mixture of molecules. And if you've managed to split them out into their 2 different components, so you've got a dish of levobupivacaine and a dish of dextrobupivacaine. If you shine light through the levobupivacaine, and remember polarized light, it's all in one plane in one direction, you will rotate that light ever so slightly to the left. And if you shine it through the dextro dish, it'll shine ever so slightly to the right. Spiffy. That's all well and good, but it gets a bit fiddlier, and I think the world decided it needed something a bit more rigid when it came to classifying enantiomers. So the second system involves counting down these molecules from the top of the periodic table to the bottom. Remember, hydrogen is the top. And if, when you count down these molecules in that pyramid, it goes from lightest to heaviest, sinking down that pyramid in a clockwise manner, then you have an R enantiomer, rectus, Latin for right, clockwise, right. Whereas if it hovers down that pyramid in an anti-clockwise manner, then it's an S enantiomer, S for sinister, Latin for left. And that's where your S-ketamine and your R-ketamine comes from. And then there's one other subtype of enantiomers, and these are stereoisomers. This comes about when the drug has more than one chiral center. And you can imagine that it just becomes a headache, doesn't it? The great example of this is atracurium. There are 10 isomers of atracurium in that ampule. If we try and imagine a molecule with 2 chiral centers, it starts behaving a little bit more cis-trans-ish, doesn't it? And you can end up with 2 of the 4 looking like opposites, and the other 2 of those 4 looking like opposites, almost like enantiomers. But then when you take one from each of those 2 pairs and compare them, oh, they're not enantiomers anymore. And you can kind of see how this happens when you think about massive protein folding in a human. Like, there's loads of things where it might be one flavour or the other. And actually, we will find out shortly that there's a bucket load of chiral molecules in a human being. So why on earth do we actually care about all this? Well, we've already somewhat alluded to it, is that these isomers have differing properties, and we as anaesthetists like different properties because we can use them to our advantage. We know that levobupivacaine is slightly more inclined to cause a sensory block, but also doesn't really take quite so kindly to the cardiac conducting system, therefore causes less mischief. It's also important to note that enzymes have specific 3D shapes, and they can often prefer one enantiomer over the other. One of the big humdingers in medicine was thalidomide. The trouble with thalidomide is that it is a racemic mixture of R-thalidomide and S-thalidomide. Now, R-thalidomide, great sedative. S-thalidomide, teratogenic, but also now has a role in chemotherapy for hematological malignancies. So half of the dose of thalidomide was doing the job we wanted it to, half the dose was not. You would think, well, why have we not just split it out like we've done with levobupivacaine? Well, unfortunately, thalidomide is a bit of a pest in that actually it undergoes in vivo switching from its R to its S enantiomer and back again. So even if you were to thoughtfully split out all the rectus thalidomide and giving a dose, unfortunately, half of that or so would be inclined to shift towards being the sinister version. And actually, the sinister version is the teratogenic version. Those clever boffins in laboratories have devised different thalidomide-like molecules that they are putting to good use for chemotherapy. Good on them. Interestingly, some cytochrome enzymes are stereoselective, i.e. they prefer one enantiomer over the other. Warfarin being a great example. S-warfarin is 3 to 5 times more potent than R-warfarin because it's not so readily broken down. Other examples of racemic drugs, we mentioned ketamine, haven't we? Ketamine is our NMDA receptor antagonist. S-ketamine is 3 to 4 times more potent regards NMDA receptor activity, whereas R-ketamine seems to cause more of the psychomimetic, paranoid, what's going on, who are you, what have you done to me type side effects. So you can imagine that everyone would love to use S-ketamine and not R-ketamine, and I can think of a few patients who I've given small doses of neat racemic ketamine to who really would benefit from pain relief from ketamine and have immediately decided that they really don't quite like this stuff. Unfortunately, you have to write a business case, it's expensive, no one was willing to cough up for that odd patient who would actually benefit, sadly. And then tramadol. Tramadol, the dextrotramadol molecule inhibits serotonin reuptake, whereas the levo molecule inhibits noradrenaline reuptake, so you need both to achieve a reasonable effect. Interestingly enough, albumin is also a chiral molecule, and therefore is a bit stereoselective in what does and doesn't bind to it, leading to alterations in free fraction of drug in plasma. I think a good example is omeprazole. Again, this is more for interest than exam content. So that was isomers, guys. Remember, an isomer is a molecule of a different configuration with the same atom makeup. We know that positional isomerism, enflurane and isoflurane are our go-to example. Tautomerism, another type of structural isomer, whereby the molecule changes shape but retains the same atomic makeup dependent on the environment it is in. Stereoisomers, subtypes geometric, that's cis trans, and enantiomers, that's our levo-dextro, sinister rotary. And we've touched on stereoselective enzymes and given some further examples of enantiomeric drugs. Thank you very much for listening, guys. I hope that you found it useful. We've smashed out the local anaesthetics chapter now. Feel free to point people in that direction if they're looking at you quizzically when you're suggesting your 2 chloroprocaines versus your prilocaines. And we're going to probably clear through the other hypnotic agents that we need to talk about to finalise the hypnotic chapter now. And then we'll probably just do a whole chapter on volatiles, so all the data is all in one place. Anyway, see you next week. Thanks for listening, guys. I hope you found it useful, but if you found it awful, do let me know. Please like and subscribe, register with whichever podcast platform you find yourself using, and leave a comment if you think I need to square something away. I just want to make sure that you guys know that every day you are getting better at this. There is a bucket of content to try and consume, and it is like drinking from a fire hose. Take it day by day, don't overcook yourself, don't freak out, and keep studying.